This is our last optimization problem. It's got to be a good one. So a ball is thrown upward with an initial velocity of 64 feet per second. So that's our initial velocity. And its initial height, h0, is 80. And so we have our formula when you're talking about feet for your position function to be negative 16 t squared plus v0t plus h0. So if we plug these in, we get this function. Okay, so now what we want to do is find the maximum height of the ball. So that means we're going to take the derivative and set it equal to 0. So negative 32t plus 64 equals 0. So negative 32t equals negative 64. That means t equals 2. So at 2 seconds, because it's feet per second, we're going to hit our max height. They want to know what the max height is. So again, we plug it in. And we see what we get. And so you can plug this in your calculator, or you can plug it in the graphing part. Go to your window, and so we are supposed to hit a max at 2 seconds. So I'm going to go a little bit farther than that because we started at 80. And if I graph it, you can see it went up and then came back down. But this is actually a vertical. I'll show you that motion in a minute. So if I hit trace and 2, we can see my max height. It's not blinking. That's perfect. 144. So max height is 144 feet. So here's what it looks like actually, though, because we're talking about a projectile. So this is shot straight up, so it goes up and then comes back down to the ground. So you want to see that again? Straight up, comes back down to the ground. And so what the parabola is doing is it's just mimicking this. So if we go back to 0, right there, time is 0, you can see that the parabola is just mimicking the height of the object. It's just a translation of it. And so we get a maximum value here right at 2 seconds and 144 feet. So that works perfectly. And there's your answer for it. So now, the good question is this. What initial velocity is required to get a maximum height of 5,000 feet? So what we have to do is make our v0 a constant. So if we take our function s equals negative 16t squared plus v0t, and now we put in 80 because we know the initial height. Now if you set this equal to 5,000, all it's going to do is give us a v0t that equals 5,000. That's not what we want. What we want to do is have a maximum height. And so we still need to do our position function with a derivative because we want to maximize it. So this would be negative 32t plus v0, and then we set it equal to 0. We solve for t, and we get v0 over 32. So now we have when our height will be maximized based on our function. So every time it's v0 over 32. So now if we plug that in to our original function, just like we would have before, see, we're just following the steps. See, up here, if you want to find the maximum height, you take the derivative, and then you find out what it is by setting it equal to 0 and solving, and then you plug it back in. So we're doing the exact same thing. But this time we're going to set it equal to 5,000. So this will give us our v0 that will maximize the height of 5,000. So this is negative 16 v0 over 32 times 32. I'm doing that because we have a 16 there. And then this is as a square. v0 squared over 32. And I can subtract the 80 over to this. So this equals 4920. Now this would become v0 squared over 64 with a negative. So I need to multiply this by 2. So we get 2 v0 squared over 64 equals 4920. And then adding that together, we get v0 squared over 64 equals 4920. We plug that in our calculator. So v0 squared is equal to 314880. Square rooting that equals 561. I'm going to put some decimals on there. 14, about 17. Sounds good. And then this is feet per second. That is our velocity we're talking about. So if we launch this at 561.1417, our object should go up 5,000 feet. and come back down. So let's check our Desmos. Okay, so I have it plugged in. I hit play, it goes up. See, it hits that 5,000 mark and comes back down. There's our parabola. If I click on it, it's going to be a little off, but you can see, oh, it's dead on, 5,000. There's even the time, 17.53 seconds is how long it took to get there. And you could even come back here now, and if we plug this number into here, it will tell us the time it would take to hit there. But you can see they're the same problem. It's just this one, it's asking for an initial velocity, so we can use it as a constant. That's it. It's just a coefficient here, and so it remains a constant in this problem. Thank you.